So today in class, we're doing 9.2. We're starting rational functions. We're going to be graphing these. So since it's a new function, let's start with our table and come up with our graph. If you guys have a highlighter, today is helpful to have some kind of highlighter handy to be able to draw all the asymptotes we're going to be drawing. All right, so first to get our graph, we're going to plug in some numbers for x here. So when I plug in -4 here, I'm going to get -1/4 for the y. And -1/2, and 1 divided by -1 is -1. What happens when I plug in 0 though?
It'll just be 0.
Well, 0 divided by 1 is 0. But what about 1 divided by 0?
It's undefined.
Yeah, that's undefined. So this one is undefined. Remember that we can always divide 0 by anything, doesn't matter, that does equal 0. But if 0's in the denominator, that's undefined. So we're going to see what that looks like in the graph. 1 divided by 1 is 1. 1 divided by 2 is 1/2 and 1/4. Okay, so we're going to graph these points so we can see what this new graph is going to look like. -2 1/2, -1, -1. 1, 1, 2/2, and 4 1/4. All right, so it might be kind of hard to tell at this point what's going on with this graph, but you can think about, you can see that these are going to get closer and closer because as we plug in smaller and smaller numbers, or I should say bigger and bigger x's, as I plug in 5, it's going to get closer, and 6 and 7, 8, 9, 10, it's going to get very close to the x-axis. Is it ever actually going to touch the x-axis though?
No.
No, it's impossible because no matter how, if I plug in like 1 billion, it's still 1/1 billion. We still have a tiny bit left, right? So this graph is getting closer and closer to this line. That is because we actually have an asymptote here. We have a horizontal asymptote at y = 0. It is getting closer and closer to this line, but it will never reach it. So it's not a part of the graph, the asymptote, but it is kind of a guideline for the graph because we know that it's going to approach that line. We also have a, oh, that's not going to work. We also have a vertical asymptote because on this side of the graph, it's going to get closer and closer as well for the same reasons. So this graph has 2 pieces. And it approaches 2 asymptotes on all 4 of these sides. So we also have a vertical asymptote at x = 0 because it's cutting through the x-axis at 0. So the domain and range for this one's going to be a little bit different because if you look at the domain, the x values that are represented, you can see the x's are going to go all the way to -infinity and all the way to +infinity. So x is all real numbers except for what?
0.
Except for 0. X is never 0. So how we're going to write that is, remember, all real numbers, we would just write negative to +infinity. Well, it is going to -infinity, and then it's going all the way up to 0, but it does not include 0. So I'm putting a parentheses. Remember, bracket means equal to. 0 means it's everything right up to 0, but not including 0. And then for the second piece, it's going from 0 to +infinity. And we put a U in between 2 of our sets of parentheses. U is kind of like a comma for us. It stands for union. It just means there's 2 parts to our domain. It's all one piece, and it's connected by this union, this U. What about the range?
Would it be the same?
It'd be the same thing, because for the same reasons, this is all going down to -infinity and positive, but we are skipping over 0 again. So it's all real numbers. You can also write all real numbers except x cannot be 0. So that's another way to write it in words. You can write it like this, or you can use interval notation. Asymptotic restrictions mean because there's an asymptote here, we had an undefined part in the table. So our restrictions are x cannot be 0 and y cannot be 0 because there are asymptotes there. There are points of discontinuity, we call it, because it's undefined there. So whenever asked for restrictions, just put a not equal to sign because that's saying what x and y cannot represent in this graph. mostly because of dividing by 0. We can't divide by 0 here. Okay, so when we graph our functions today, so this is the parent function. We're going to be practicing doing transformations just like we have with all of our functions. So how does K shift the graph for all of our graphs?
Sorry, I'm taking my dog out to the bathroom right now.
Oh, that's okay.
It shifts it up and down, right?
Yeah, K shifts up and down. And so since it shifts it up and down, that's going to shift our horizontal asymptote up and down. Because think about the vertical one, this shifting up and down is not doing anything. So this one is going to shift the horizontal asymptote like this up and down. Okay, so when it's positive, it's going to go up, negative, it's going to go down. Now, H is the one that shifts left and right. And remember this one, because of this minus, always moves the opposite of what you would expect. So because if it says plus H, if it has a positive number here, we know that it's moving to the left. And if it's negative, it's moving to the right, just like all the other functions. And this one is going to shift our vertical asymptote left and right as there's numbers plugged in for H. And then A does the same as it did for every other function. Remember, if A is negative, that means it reflects over the x-axis. So think about what that means for this graph. If it reflected over the x-axis, what would that new graph look like? See if I can get a different color.
I feel like if they switched quadrants.
Yeah, it would switch quadrants. This piece would reflect down here. And this piece would reflect up here. So that's what it would look like if it was reflected. It would just switch to the other two quadrants. Also, if A is greater than 1, remember that's a vertical stretch. So if we have numbers in here, it'll move this key point up or down. So put a star on this key point because this is how we're going to draw our graphs. It's always right in the corner of our asymptotes. Notice it's over 1, up 1 in both corners of the asymptote. And this key point is the one we will move around if we have to do a vertical stretch. We typically don't have a vertical compress with this function because that would be like a fraction on a fraction or a decimal on a fraction, which you don't see. That would not be simplified version. So you won't see something like that. It would be in a completely different format. So this is what we're going to practice today, is doing transformations on this parent function. We're going to apply numbers in for H, K, and A and be able to graph it and find these features. So let's practice a couple. All righty. So first, this plus 2, remember this is in the K position, so that's shifting things up and down. So the graph is shifted up 2, which means my horizontal asymptote is shifted up 2. Oh yeah, I like this graph marker. And this 1 shifts the graph to the right 1, which means my vertical asymptote is shifted to the right 1. And we have no stretch or compress because it's 1. 1 is just like default. So now we have enough information to draw our graph because we know if this is where the asymptotes are, our key point is over 1, up 1 in both of these corners. And we can draw our swoopies from there. It's going to swoop into both asymptotes, approach both asymptotes on either side of this graph. So that's a good estimate of what that graph would look like. We have a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 2. So once you know where the asymptotes are, you're able to figure out where the domain and range is. So the domain is all real numbers except for which one?
0.
Not 0 on this one.
Oh.
What number are we skipping over on this one? Because look at the asymptote is moved this time.
1.
Yeah, it's skipping over 1 this time because that's where our new asymptote's at. So it's skipping over 1. So it's all real numbers from negative to positive infinity, but not including 1 because there's an asymptote there. And we can see it's getting close to 1 on both sides of the graph, but it's never going to be equal to 1. All right, the range is going all the way to negative infinity and positive infinity, except for it is skipping over 2 because there is a horizontal asymptote there. So this is how your domain and ranges will look if you write it in interval notation. You can also write it in words, but I'd like you to practice writing an interval notation so that it becomes familiar to you. And then the restrictions, remember, means the same as just where the asymptotes are, because in this example, x cannot be equal to 1 and y cannot be equal to 2 because there is an asymptote there. So when we write it as a restriction, we just put the not equal to signs there. Questions so far? Make sense?
So whenever it's the parent function, neither of them can equal 0, but whenever they're transformed, it's the number that it's like, whenever you write the transformation, like the y can't equal to, I don't know how to word what I'm saying, but like.
Yeah. Yeah, so these numbers in the equation are going to tell you where the asymptotes are.
Okay.
Which helps you figure out the graph and where the vertical and horizontal asymptotes are.
And where they can't land on, right?
Yes, and we know that if there's an asymptote there, the graph is not on that number. It's a guideline. It approaches that number, but it will never equal that number, whatever that number the asymptote's at. So it will never equal 2 and it'll never equal 1 for the x. It's just getting very, very close to it.
Okay.
All right, let's try another one. What transformations do you guys see in this equations? What's happening to the graph?
It's
gonna
being
stretch.
vertically
Stretch is 1, vertical stretch by 2, and what else?
and it's moving
Down.
it's moving down 1.
I agree. Down 1 from this -1. So we're going to draw our asymptotes first. If it's down 1, that's going to be our horizontal asymptote. So down 1.
And
And
then
it said nothing about left and right. So where do we put our asymptote vertically?
0.
It just stays at 0. It's just going to stay there. Now, since it's vertically stretched, remember the key point is over 1 up when it's normally in this corner right here. But since it's vertically stretched, I'm going to go over 1 up 2 and just put it up here instead. And same with this one. In this corner, I'm going to go down 2. So when you stretch it, the A value just tells you how many to move from there. Default is over 1 up 1. And then the A value, if it's bigger than 1, you'll go up 2, 3, 4, and so on. And then you can draw the swoopies from there into all of the asymptotes. So we have a vertical asymptote at x equals 0, horizontal at y equals -1. So that tells us our domain and range. The domain is everything but 0. And the range is everything except for -1. And the restrictions, of course, are x cannot be 0 and y cannot be -1 because there are asymptotes in those 2 spots. All right, so you will practice some graphing on your homework. Now, on the last example, it has a graph, and your job is to find the equation this time. So we're going to go the other way around. Now, a big tip is to draw your asymptotes in, because that's really going to help you figure out where the equation is going to be. So remember, the asymptote cannot, it should go through both pieces of the graph. So draw where you think the asymptotes would be so that it is going through both pieces of the graph. And mine looks like it's going through 2 for the horizontal asymptote, y equals 2. And the vertical looks like x equals -1. If I look at where the asymptotes are. So I can write an equation with that information. Oh, I also should check to see if I have an a value to see if it's stretched. But I'll come back to that. First, let's do the asymptotes. So h is the one that's shifting it left, right, and I can see it is left 1. So remember, we're going to change the sign of the h, which makes it a +1. H is always the opposite sign. K, it is shifted up 2, so I'm going to put in a +2 for the K. And then let's look at the A value. Default, remember, it would be right here in this corner, and it's clearly not. So how many, I'm going to go over one. How many do I have to go up to reach that graph? It looks like 4. I'm going to check the other side. Over 1, 1, 2, 3, 4. Yeah, I have to go up 4 to reach the graph. So that tells me it is vertically stretched by 4. And we already said that it was left 1 and up 2. All right, from there we should be able to find the domain and range. The domain is all real numbers except -1. And the range is all real numbers except y cannot be 2. I guess I should put this x cannot be -1 there. All right, it added a couple features on this one. It asks for the X and Y intercept. So the X intercept is when it's crossing the X axis. So we do have an X intercept here at -3, 0. Remember, when we have an X intercept, the Y is always 0. That's going to be helpful when we're going to do it from the equation in just a minute. So don't forget, anytime it's crossing the X axis, Y has to be 0 if it's on the X axis. And same with the Y intercept. That means that 0, X has to be 0. And we have one right there at 6. So by looking at the graph, you can see the X and Y intercept. I'm going to show you how to do it from the equation on the next example. Any questions about graphing before I do X and Y intercepts from the equation? So far, so good?
Mm-hmm.
So next class, we're going to do more rational functions. They're a little bit more complicated because they will not be in this format. They are going to be one big old fraction. And so we're going to learn how to break them down to be able to find the features to be able to draw the graph. So one of the basic features that we're going to learn today is how to find the X and Y intercepts. So as I had said before, if it's crossing the X axis, that means Y has to be 0. So I'm going to plug in 0 for Y. Because if I'm finding an X-intercept, I know Y has to be 0. So if I could solve this equation, I could figure out what the X-intercept is. Any ideas on how to solve this?
No.
What is this symbol right here? What operation is this line?
Division.
It's division. And how do we undo division?
Multiplication.
We multiply. So if I multiplied this by x plus 3 on both sides, that clears that out, right? So now I'm just left with x plus 2 on this side. What is x plus 3 times 0?
0.
Still 0. Now I have an easy equation to solve, right? I can subtract 2 and x is equal to -2. So the moral to this story is whenever you're finding the y-intercept, this denominator will always multiply away because no matter what is down here, it doesn't matter if it's the biggest polynomial ever. When I multiply it times 0, it's going to go away. So all you have to do is set the numerator equal to 0 and solve for x, and you will always have the x-intercept. So my x-intercept here is -2, 0. All right, now we're going to do the y-intercept. The y-intercept, if it's crossing the y-axis, that means that x is always 0. So I'm going to plug in 0 for all the x's. Plug in 0 for all the x's and simplify. So 3 times 0 is 0. 0 squared, still 0, plus 2 times 0 is 0, minus 3. So what's 0 divided by negative 3?
0.
Just 0. So we have a y-intercept at 0, 0. So whenever you're finding the y-intercept, you can just plug in 0 for all the x's and simplify, and you'll know where the y-intercept is. All right, these are 2 good practice questions. You can check my key to practice those 2 questions, but I would like to do a couple transformations. We have done function notation before, but I wanted to review it. So if I take the function and add 2, how is that going to move the graph?
Just to the right, too.
It would be to the right if it was, remember, right and left is when it's in parentheses like this one.
I meant up 2. Sorry.
Up 2 is correct, yes. Since it's outside parentheses, this is just going to shift it up 2. So now they want us to think about how would that affect our rational function. So our vertical asymptote, if the graph is just moved up 2, is that going to affect the vertical asymptote?
No.
No, so it's going to stay at x equals 0. Now the horizontal asymptote, if I shift it up 2, my new horizontal asymptote is going to be y equals 2. So that's what they're wanting you to do in this section, is just say, okay, what's the transformation and how would it affect the asymptotes? So let's choose another one. How about this one right here? 4. What is this transformation? 4 times the function.
A vertical stretch of 4.
Good. Vertical stretch of 4. And so how is that going to affect the asymptotes?
It won't.
It doesn't affect either one. You're right. Because if we stretch it, it's really just going to affect that key point. But the asymptotes are going to remain at 0. They will stay the same. All right. Last thing I'm going to show you today is today all the functions we've studied are in this format. And this one is not in this format, but there is an interesting way that we can divide these to get it into this format. And we just did long division and synthetic division, and you can use that to rearrange it. So let's review synthetic division to get it in this format. So remember, whatever we're dividing by, if it's x minus 1 or plus 1, we can use synthetic division. So I would do the opposite of this, which is a 1. I pull out the coefficients. So the coefficients in this case are just 1 and 3. This is a little baby synthetic division. And then remember, for synthetic division, we drop down the first number and then multiply, add, multiply, add. So multiply and add down. So it is always 1 degree less than what we started with. We started with an x, so that means this is just a number. This is just 1. And this is our remainder. So the answer is 1 plus the remainder. Remember, we write the remainder over what we're dividing by, which is x minus 1. So if I rewrite this equation, I'm going to put this term first. That's a positive 1. I just switched those 2 terms around. Now look, it is an equation that is in this format. I can see that I have a horizontal asymptote at 1, a vertical asymptote to the right 1, and it is vertically stretched by 4. Isn't that kind of cool to see how it connects? I think it's kind of fun. All righty, so that is all I have for you guys today. Any questions on this?
Will it tell you what equation they want you to use? Like, if you don't actually have to solve for it, if it's just for the x-intercept or the y-intercept, could you just solve for that?
Which ones are you talking about? From the graph?
Yeah, like if they ask you to solve for like the y-intercept, could you just solve for it?
Yeah, any problem that it gives you and it asks for the y-intercept, and this works is for any function. If it asks for the y-intercept, you can always plug in 0 for x and find the y-intercept. That works for any function that we've studied this whole year. That always works.
Okay.
So it doesn't matter what format it is in, what function you're solving. It will always give you that. Like, think of a function like this. If I want the y-intercept, I can plug in 0 for x. 2 times 0 is 0 plus 4. And you guys know that the y-intercept is 0, 4 here because that's in y equals mx plus b format, right?
Mm-hmm.
Same if I had a quadratic function. I plug in 0 for x, I get the y-intercept of 0, 4. So you can always plug in 0 for the x's to find the y-intercept for any function. It's a good rule of thumb to remember. Same for the x-intercept. You can always plug in 0 for y to find the x-intercepts. Other questions?
On the homework?
Yes, ma'am. 9.1?
Yes.
Sure.
So this sounds weird, but I really understand the inverse variation, right? Is that what it's called?
Yes.
Okay, but I don't understand the direct variation.
Well, the good news is that one I'm least concerned about. It's not on your progress check and it's not on your test. So there's the good news. But the direct variation should be easier because it is just, instead of this format, you are using this format, okay? Instead of the constant being divided by x, the constant is multiplied times x. That's the only difference. Other than that, you do it the same.
Okay.
So like number 2, did you do number 2?
I just skipped it. I skipped number 2 and number 10.
Okay, let's look at number 2. So the cost of pizza varies directly with the square of its radius. I'll just call that r. If a pizza with a 6-inch radius costs $8, how much should a pizza with an 11-inch radius cost? All right, so to solve for you always solve for the constant first, and then you answer the question. So to solve for the constant, I'm going to divide both sides by 6. My constant is 4/3. So that means my equation is my cost equals 4/3 times the radius, whatever the radius is. And in this case, the problem they gave me, yeah, this was the radius, is 11. So 4/3 times 11 is 44/3. And how much should it cost? So I probably shouldn't say, well, that'll be 44 over $3, ma'am. I probably should write this answer as a decimal considering it's talking about money.
Mm-hmm.
So let's see, 3 goes into 4 one time with 1 left over. So 3 goes into 14 4 times with 2 left over, right? So that's 2/3. 14 and 2/3, what's 2/3 as a decimal?
Approximately 0.67.
Yeah, so 67 cents. So $14.67. Does that make sense?
Yeah.
So the process is the same for the direct variation. It's just the initial setup of the equation. If it's inverse variation, you know that the constant is being divided by x. If it's direct variation, the constant is multiplied times the x.
Okay.
Anything else on the homework? All right, well, finish your 9.1 progress check today, and then you can start on 9.2 practice problems. And if you have time, you can do that progress check today, but that one will not be due until Wednesday. All righty.
All right.
Well, good to see y'all, and I'll see you on Wednesday.
Good to see you
Have a
too.
good day.
Bye-bye.
Bye.